So, did you check your score in the previous exam? And also you got your homework score. So some people, they reached out to me and said that they had some special requests. They wanted to see whether they can have some reading or not. I hope I explained some of them by email. So the basic thing that people often have noticed is that whether you like the problem. So let's say you have a problem and you find out what is the corresponding answer. And when you start with the homework or the quiz, you get your result, and then you realize, oh man, actually I wanted to answer that, but instead of that I answered this. I mean, that's totally okay. This happened to me as well, so it's not that you have something new. So let me try to explain that how, after getting an answer, how you're going to cross-check. How would you know that your answer is correct? How does it make sense? So let us say that you're trying to find out the electric field for the circular shape of ring of charge, and you got some expressions. Let's say this is the electric field, and you found out that electric field is proportional to K, then let's say this is U, and this is your H. Let us say that you somehow did your math and you figured out that the electric field distribution for a ring of charge is the following. Now, having get that result, how would you know that you have not made a mistake somewhere in the process?
Hope.
Yeah, hope is one thing, and hope is a good thing, of course. But apart from hope, we also have some support from logic and reasoning and argument. So what are those arguments? The argument is the following. You always think how your electric field would look like if you take your coil further away or further close or maybe somewhere in between and try to see whether instead of using mathematics you can use your intuition and see whether your intuition matches with your mathematics or not. Okay? For instance, one of the simplest things to do is to just check what happens if you take your coil far away, very far away, and see whether the electric field is going to reduce to zero. Right? So everybody knows that if you take your coil far away, then the electric field will be zero. Right? So just check this first thing. If you take this point far away, that means you are taking the value of h to be infinite. If you put your value of h to be infinite, what's going to happen? What is the electric field for this case? Let's say that you figured out that this is the expression of the electric field, but you found out that if you place h to be infinite, I want to see whether electric field really goes to zero. So you plug in this value here. And you get this result. From there, can you tell what will be the next step? I just plug in the value of h to be infinite in this case. Would it reduce to zero or would it go to infinite? We have infinite in both cases, in both numerator and denominator, right? So what will be the result? Will it be finite? It should be 0. If it is not 0, then your result is wrong. Correct? But now we have a problem. We have infinite in both top and bottom. But let us see that how does this h go to infinite. Let's say that we keep h as is and try to see how the electric field changes as we increase the value of h. We cannot directly plug in the value of h to be infinite, then we have a problem. But if h increases, let's say h goes up, then the numerator, it goes up also, right? How does it look like? If I just keep all of these constants and only change the value of h, how does the corresponding electric field go up? How does the curve look like? If all of these remain constant, then this curve will be just a straight line, right? I'm just trying to plot k rho h. So k rho h would simply go up like a straight line. You follow? How about the bottom one? This guy is a summation with b square. B is the radius of the circle. So if h is really, really large, you may assume that this b square is not really contributing too much. Okay? So h square plus b square will be pretty much equal to h square. Just to simplify, we're just trying to see that how our idea plays out. So if h is really large, I'm going to ignore this b square term. And how about the bottom one? H square, that is raised to the power 3 over 2. So that means it's actually h to the power 3, h cubed. So the denominator, that would raise like this, right? So this is actually b square plus h square raised to the power 3 by 2. And again, as I say, that I did not really care about b square because I know that I'm trying to find out the value of e when h is very large. So even if b square is there, it doesn't make my curve too much different. So this guy, it goes almost h cubed. This guy, it goes just proportional to h. So this means, as you keep increasing the value of h, which one will win at far away? The numerator or the denominator? So this is the numerator. This is the numerator. And this guy is the denominator. So which one blows up? The denominator. Despite you have h in both top and bottom, but the bottom guy is going to increase much faster compared to the top guy. So that means if you take h to be infinite, e is not going to be infinite. E is going to be 0. Do you follow the argument? That why it is not infinite, why it is 0? The numerator does only go up linearly. The denominator, it goes up the denominator goes up cubically, h to the power cube. So this is how I know that my intuition matches with my actual mathematical result. That's one thing. What are the other things that we can check? We can also check what happens when electric field is taken to a point which is close to its center. So we know that if this point is at the center, then the contributions from all of these guys, all of these segments, if you add them up with a vector, they are going to cancel out at this point. Right? So at the center of the point, in the center of the circle, there shouldn't be any electric field. So that means when h is 0, your electric field is supposed to be 0. Now let's check whether your expression actually tells that. If h is 0, just plot h to be equal to 0, then this guy is 0. How about the bottom guy? The bottom guy is b cubed, right? Take h to be 0, so the entire term would reduce down to 0. So this means for h equal to 0, electric field is really 0. Right? So we checked two different conditions, and it matches with our intuitions. That if you take this point too close to center, it's 0. If you take it too far away, it's also 0. So this means if you try to draw the electric field over H, we know that H, when H is 0, electric field is 0. When H is infinite, electric field is also 0. So it must be something like that. As you increase the value of H, electric field should go up, reach a maximum, and then drop down to 0. Right? So there should be an optimum point. There should be a point where E is equal to the maximum value. Okay? And look at this particular point. This is a margin, and above that margin, this guy, this ring of charge, it behaves like as if it's a point charge. You know that a point charge behaves like that. If you take a test charge farther away from the point charge, its impact reduces, right? So you look at this guy. This part, it actually tells you that it's acting as a point source. But this guy is a different behavior. It says that a ring of charge really behaves like a circle. So on that part, it's actually a behave like a point source. And on this part, it behaves like a circle. Do you follow? Let me know if you have any question for this point. That why we are saying that a ring of charge, if you remain close to the ring of charge, then it really behaves like a circle. But if you go far away from the charge, it will behave like a point source. When it behaves like a point source, its impact diminishes as you increase the distance. When it behaves like a charge, when it behaves like a circle, its impact increases as you go further away from the center. Okay? And this is the transition point. Now tell me this. If I increase the size of the circle, if I make it bigger, would this point go to the right or to the left? Think carefully. And let me ask the question one more time. Let's say you take this ring of circle, you keep everything else same, you keep the charge density same, but you increase the size. So now it's a bigger circle. If it's a bigger circle, whether this E equal to Emax point go to the right or to the left?
Left, right?
Go to the left. If it is a bigger one, why?
The dependency on B is in the denominator. So the hypotenuse is bigger.
So if you look at this expression, and by expression you were saying that since I make my B larger, that would reduce, that would take these guys further away from here to the left. But do not look at the equation first. Think about your intuition. You are making this circle bigger. Do you expect this guy to behave like a point source or a circle? Circle. If you make it smaller, then it behaves more like a point source. So if this guy becomes bigger, this particular line, transition point, should it go to the left or should it go to the right? It should go to the right, because it behaves like a circle. It behaves like a circle more. So in order to make it look like a point source, you have to go further away. If you go further away, then this guy, this would shift up to its right. So in other words, for a bigger circle, this is how the electric field versus the distance would look like. So it says that if you make the circle bigger, then in order to make it look like a point source, you have to go further away. You follow? Is it getting too complex? Now let us see whether our result actually supports that idea. So it says, if you take the value of B to be larger, then electric field is gonna decrease, right? So something is not right. Something must not be right. Maybe somewhere I made a mistake. I think the actual answer is this. Okay? If you plug in that answer, and I think probably we have to multiply it with a factor of 2 pi. That you have to check. Okay? Go and check your book. But what I did wrong is that previously I did not include this term. And that's why I get a wrong answer. But there is no way, I mean, the only two ways to find out that possible mistake is the following. That one, you go and check all these detailed mathematical calculations and see where you have missed something, a term. But the other way, the more practical and fruitful way, is to check your intuition. Okay? Like, what happens if I take this point further away, or too close, or make this circle bigger, something like that, and see whether your intuition matches with your final result. So when you say that whether E equal to E max should go to the right or left, don't make a judgment based on what you got. Make a judgment based on what your intuition says, and then check whether your actual answer matches with your intuition. If it doesn't match, something is wrong. So go and check one more time. Are you following? All right. So let us see. So the other day, on Thursday, we talked about Gauss law, and using the Gauss law of divergence, we figured out that the electric field for a point for a sheet of charge, a very large sheet of charge, at a point P at a distance, let's say D, is the following. Electric field is rho divided by twice epsilon, where rho is the charge density on this sheet of charge, and epsilon is the permittivity of the medium. And we also say that if we take a long piece of wire with charge density rho, then at a point P at a distance D, the electric field is going to look like P root over twice Kp divided by, I already forgot. Can you guys check your previous class note and help me out? So what would be the denominator in this case? I know the denominator should contain the term D, but I do not remember that whether it contains some other term here. Some of the constant term might be there. Okay? Is it how it is? Okay. So anyway, the most important part, even if there is a constant, don't worry about the constant too much, because most of the time we care about the variable. Okay? The variables here is D and rho. So these are the most important part. And we also know that in case of point source, the electric field is just kq by d square. When we started to discuss the interesting idea that why electric field is 1 over d square for a point source of charge, but it reduces to 1 over d for a very long line of wires, and there is no d term if it is an infinite sheet. So it says that if you take a point further and further away from a sheet of charge, the electric field is going to remain same. There is no change. So we want to understand why it's like that. Our mathematics helps us to get to this point, but how do we intuitively understand that this is true? wanted to answer this question. Let us try to see what happens for a very long piece of wires. If we have a very long piece of wire, we know that all of these segments is going to contribute a little bit on this electric field at a point P, right, at a distance P. Now, the segments that are very close to the center of this wire, their contribution would directly along the x direction, right? However, the segments which are further away from the center, for instance, this guy and this guy, they are further away from the centers. And that's why, if you look at the contributions, you see that they are, the vectors of their contributions are angled with the x-axis, right? And that's why they have both x and y component. The y component is going to cancel out, but the x component would add up. What happens if you take some segment which is even further away, much further away from the center? If they're really far away, then their contributions would have more y component. So more contributions is going to be cancelled out. And very little amount of effect will be there along the x directions. So these guys, which are further away from the center, their contribution is very little. The guy which is at the center, their contribution is more, right? So what if you change this guy from this point and take it up there? You change the distance between the point of test charge and this long segment of wire. What's going to happen to those contributions from these distant sources? Now these guys, previously they saw that this point was very close to them, and that's why their y contribution is going to cancel out. But if you take this point further away, now these guys, their contributions will be more aligned to the x-axis, right? So the further you take this point from this piece of wire, these contributions are going to align up with the x-axis. So this means that this contribution is going to increase because they have less y component and more x components. So this is the interesting part here, because it says that it might be possible that if you take this guy further and further away, these contributions will actually increase because they are more aligned. And this is exactly what happens in case of a wire and in case of a sheet of charge. In case of a sheet of charge, if you take this point very close, then most of the contribution comes from the center. The guys which are further away from the center, they do not contribute too much because their y component is going to cancel out. But if you take this point further away, then these guys which were further away from the center, they increase their contributions. Okay? And this is why the electric field for this sheet of charge, it becomes independent of T. Let me repeat this thing one more time. If you take electric field very close to this sheet of charge, most of the contribution will come from the center. If you take electric field further away, then most of the contribution will come from the segments which are further away from the center. And that's why they balance in such a way so that electric field eventually does not depend on the direction and the distance of T. Do you follow? Alright, so let us see if I take, let's say you are working on your lab, okay, we were working on a transistor design, and you were not careful enough, so maybe one of your hair, it fall down, it fall on the piece of device that you are working on. And your hair is probably 1 inch long And the thickness of the wire, the thickness of the hair actually, is 50 microns. That's typically the dimensions of the sizes of human hair, like at least the boy's hair. So let us say that the device that you are working on it contains a lot of devices, small transistors. So each of these segments, they contain some devices. And let's say that each of these small squares, they have a dimensions of 10 nanometer by 10 nanometer. Okay? So you know that your hair is gonna contain some charges. And let us say that your hair has a positive charge. Let's say 1 coulomb charge is there. Okay? So to explain the scenario one more time, you are working on a device. This device has a lot of squares. Each of these squares contains some transistors. The size of the square is 10 nanometer by 10 nanometer. A hair falls down on the piece of devices. The size of the hair is 1 inch in length and 50 micron in width in the diameter. And this hair, this piece of hair, it contains some charges. The question is, how you would model the effect of your hair on the piece of squares? Would it be a point source? Would it be a line of source? Or would it be a sheet of charges? So would it be a point charge? Would you model your hair as a line of charge? Or would you model your hair as a sheet of charge? Answer very carefully. All the dimensions are there. Take your time and tell me that how should I model your piece of hair in terms of these ideal sources? Let us try to exclude what possibilities are not viable. For instance, would anyone try to model this piece of hair as a point charge, as a point source? Probably no. So this guy goes out. So we have two more candidates. Either this piece of hair would be an infinite sheet of charge, or that would be a very long line of wire. What does the intuition say? Sheet of charge? Why is a sheet of charge? To me, it looks like a long wire, piece of wire.
Trick question.
Trick question, yeah. If it was that simple, then I would have answered it. I mean, I would have asked it. So let us look at the dimensions. So I'm saying that each of these square boxes, these are 10 nanometer by 10 nanometer size, right? Your hair is very long, of course, but look at the width of your wire. It's 50 micron. So 50 micron, how big 50 micron is compared to 10 nanometers? How big?
Pretty big.
So 50 micron, that means 50 multiplied by 1000. And 10 micron, so 10 nanometers. So how big is this? Right? So it's that big. 5,000 times bigger. Right? So despite it might be tempting you to model this piece of hair as a long line of charges, it's not actually a long line of charges. It's actually an infinite sheet of wires. You follow? It's an infinite sheet of wires. So use this guy. And remember that all of these wires, no matter how far they are always going to experience the same amount of electric field. Always. Because electric field for infinite sheet of wire does not depend on the distance. Okay? You follow? So if I ask you a question in the exam and give you a piece of hair, very carefully look into the corresponding dimensions and then make a decision. If these dimensions are very, very small compared to the other dimensions of your hair, then of course it's a sheet of charge. But instead of 10 micron by 10 nanometer by 10 nanometer, if I give you 10 millimeter by 10 millimeter dimensions for the devices. So each of the squares, they have the dimensions of 10 millimeter by 10 millimeter. Okay? How we would model this piece of hair? Is it a wire? I say that this guy, the length of this hair is 1 inch. So 1 inch is how many millimeters? 25. Just 25 millimeters. Right? So if it is 25 millimeter, if each of your device is 10 millimeter by 10 millimeter, would you say that this is an infinite line of squares? No, it's not an infinite line of squares. Now it's a finite line of squares. If it is a finite line of squares, then the electric field would be twice K rho by D multiplied by these other factors, L divided by root over L squared by B squared. Okay? So the bottom line here is that be very careful when you are trying to model something into the idealistic mathematical abstractions. Whether it's a point source or whether it's an infinite sheet of wires or whether it's a line of charges, everything depends on what you are really working on. What is their device dimensions? Okay? Very careful about it. Yes, go ahead.
So where is the point where we can definitely say, okay, we need to use sheet of charge, we need to use line of charge? Like it seems like there's some
Yes,
gray area.
absolutely.
Like
Very
where
good
is the
question.
point?
So this means, very good question, I appreciate that. So this means that there might be some gray areas where you may not be able to determine whether it's a sheet of charge or whether it's a line of source or whether it's a point source. So for these gray areas, you need to do the mathematical modeling. For instance, this particular guy is the exact mathematical modeling. If you plug in any value of L, it will give you the right answer. Right? For instance, if you take the value of L to be infinite, this mathematical model is still going to give you the right answer. But I know that if I want very close to this piece of air, I don't need to consider that L is infinite. I can simply use this guy, and my answer will be very close to the right answer. Okay? But for those gray areas, when you cannot make a determination, then you go and make a true mathematical model. That's why we have simulation softwares. Okay? The softwares actually take care of all these details. But most of the time, believe me, most of the time as an engineer, what you need to do is to make a very quick judgment. Very quick judgment. Going to the software and running the software and making sure the software is actually doing the right thing, it takes a lot of time. And time is precious. So when you go out and really start your professional life, you will be valued if you can make your decision like that. So make your decision in a split of a second and you will be valued. Because if you cannot make the decision, then what are the other opportunities? What are the other options? The other option is that you engage a team. They will take 1 week or 1 month to solve this problem and come up with that. But by the time you lost your time, you lost your money. What if you can make a quick judgment and say that, okay, I mean, I don't need to make a quick model. I just know that this guy is going to behave like that. That is the appreciation. Okay? So make sure that you culture your intuitions, understandings, and see that how you can use your judgment very fast. All right? So in our class we talked about a lot in terms of electric field. But I think a more common term that is known to all of you is probably not the electric field, but the voltage. Right? Do you know what is the voltage of these power lines? Like if you plug in a multimeter on those sockets,
120.
120 or 110, something like that. And do you know what is the frequency of this power? 60 hertz. Okay. So the transmission line that goes over our head, those could be much more higher voltage. Those could be much more, especially if they are further away. Typically, they have a much higher voltage line and they have very little amount of current. So the term voltage is very well known, I believe, to all of you guys. Now, how voltage and electric field are related to each other? Let's start with our known scenario. Let's say we have a power socket with 2 poles, and we know that if we plug in a multimeter between those power sockets, we will get a value which is V equal to close to 120 volt or 110 volt. What does this really mean, and how electric field is going to be related to this guy? So it really means the following, that you have positive and negative charges on those 2 holes. Okay, maybe those are plus Q and minus Q, and because those are charges, there are electric fields. And those electric fields are spanned from positive charge to the negative charge. Okay? The direction of those electric fields will be from positive to negative. So they will have an arrow in this direction. Okay? So those are the imaginary electric field lines. And if you try to take a test charge from this side and move it up to the positive charge, the amount of work that you need to do is equal to 120 joules. Let me repeat what I said. We know that these 2 holes have a voltage of 120 volt. It means the following. If you take a test charge of 1 coulomb and try to take the test charge from here, from the negative charge guy to the positive charge guy, the amount of energy that you need to spend is 120 joules. If you move a 1 coulomb charge from negative charge to the positive charge inside the power socket. Okay? So in terms of mathematics, how do we write it? We write it in the following way. We take the integration of electric field over the length. The length means the path where you have taken the test charge from negative charge to the positive charge. So let us say that we have our positive charge here and our negative charge is here, and we take a test charge of 1 coulomb from negative charge to the positive charge. Then this is your L. Okay? This is the direction of your L. And because there are charges, we have some electric fields. And that electric field should have a vector dot product with the L. And if you take the integration of electric field over the length L, you will get the corresponding voltage V. Okay. Now, interesting thing here is, what if instead of taking the test charge through a straight line, what if I intentionally choose a very roundabout way? Let's say that I take a point charge and take it like this and go up to this point. How the corresponding integrations look like? If I increase the length L, so instead of taking just a shortcut, if I take a very long route and eventually go to the other side, how this electric field integration will look like? Can you guess? Is the same? So let us try to see a corresponding mechanical example. If I take a piece of object and I elevate this piece of object directly from the ground to the top, you know that we are going to introduce some potential energies on this object, right? And how much potential energy will be there? The amount of potential energy will depend on how high this object is. So if I take this point and elevate it from ground, let's say that I elevate it by height of h, then the potential energy would gonna be mgh. Okay, mg means the weight of this object, and h is the height. Now, instead of directly lifting it upward in the vertical direction, what if I go in this way and move it up to that length of h? What would be the corresponding potential energy stored in this object? Would it be same or different? It would be same. So it all depends on what is the eventual vertical distance from the initial point to the final point. It doesn't really matter that in which path I take this. In a similar way, when we calculate the voltage, electric voltage, it really doesn't matter that which path I choose to take my test charge from negative charge to the positive charge. All that matters is what is the shortest point of distance between negative charge to the positive charge, and that will give you the voltage. Okay? Even if your length is very different, still, as long as the initial point and the final point remain same, you should always have the same voltage. Okay? So this is why when you plug your device with a long piece of wire on this power socket, let's say that this is a power socket, and your device is maybe somewhere here in the corner of the room. Let's say it's a microwave oven. So it really doesn't matter that where the microwave oven is. All that matters is that how much charge is transferring from the positive side to the negative side. And it really doesn't matter that which length does it follow. Even if you bring your microwave oven very close to it, maybe you have another piece of instruments. Very close to this power socket. It will still have the same voltage. Despite a charge will take a different route to go from the positive side to the negative side, these two guys will have the same voltage. Despite their path is very different. Do you follow? So this is why voltage is a scalar quantity. Voltage does not matter that which length you take, which direction of route you take. But this electric field, this is actually a vector. It really depends on which path you are taking. Okay? So we understand that voltage is a scalar. Voltage is expressed with a dot product between electric field and the path you take to take a test charge from negative side to positive side. If you integrate that, you will always get a scalar quantity. It doesn't matter that which path you take, you will always have the same voltage. Now tell me the other thing. Let's say you take a mechanical object, move it up from the ground, and then you put it back to the ground again. So you take a circular path. You go up, then you go down. What would be the corresponding change in potential energy? 0. If you go to a circular path and come back to the same point, as long as your initial point and final point is same, the potential energy won't change, right? In a similar way, if you take a test charge if you go from negative source to the positive source and come back again to the negative source, the eventual change of voltage is 0. Okay? So, if you take a circular path, which is represented by this circle over this integral shape, it will always be 0. Okay? The circular integration of electric field over any path is 0. Okay? So this is why when you calculate the total voltage of a circuit, let us say that you have a battery, and then we have some resistance, we have some other inductance, and something else might be there also. And we have voltage. Then the total voltage, if you go around this loop, would be 0. In other words, let us say that we have a battery of voltage V, and if the battery is connected to this resistance and inductance, let's say that this guy has the voltage of VR minus, VR plus minus, and this guy has the voltage of VL plus minus, then we can say that V is equal to VR plus VL, and that means if you add them up together, keeping their sign fixed, then the total value of this voltage will be 0. Okay? Take all of them together, add them up, making sure that you are taking care of the sign, then all of them will add up to 0. So this result and this result are exactly the same. Okay? Have you seen this kind of expression? It's called Kirchhoff's law. Is it familiar to you guys? It is. Okay. So I'm not going to elaborate on this, but I believe that you have seen this if you take a course on network theory or DC circuit. You should be familiar with this expression. But the origin of this equation, it comes from here. That if you take a circular path for integrating the electric field, the total value of voltage is 0. You start your journey, but come back to the initial point. There will be no change in your voltage. Right? So, we learned how to calculate voltage from electric field. In a similar way, we can also find out electric field from voltage. And in order to do that, what we need to do is to take the differentiation of voltage with respect to space. So, you know that voltage, let me write it one more time. Voltage is the integration of electric field over the length. And electric field is the differentiation of voltage over the space. Okay? So, if you are given a voltage, you can also find out what is the corresponding electric field. So notice that I just wrote x in the denominator. But in case of a 2-3-dimensional space, we need to take care of both x, y, and z dimensions. So in case of both x, y, and z dimensions, this guy becomes a little more involved, and the way we write it is the following. We take not only x variations, but we also take y and z variations. So this is why in case of 3-dimensional space, we write it in the following way. So this guy is only for 1-dimensional case. And this guy is for 3-dimensional case. Okay? So one more time. If you want to find out electric field from potential, you have to differentiate that potential field with respect to x, with respect to y, and with respect to z, and then you add them up together. You will get the total electric field. Okay? So, in mathematics, we typically use a shortened formula for these expressions. Instead of writing this long expression, we simply write it as an operator. This is called a gradient operator. So if we take the gradient operator of the potential, you get the electric field. But basically, it just means the following, that I'm just too lazy. I don't want to write this entire term. If I give you this term, you will understand that this guy is actually this. Okay? You take the derivative with respect to x, y, and z, you add them up, making sure that they have the right magnitude and right directions, and you will get the total electric field. So electric field is often expressed as the gradient of field. Okay? Again, what is gradient? It's just this. This is the gradient. It's just a shortened formula for writing what we are trying to integrate. So, to give you an idea that how the gradient of a potential field would look like, a gradient of a potential field always looks like the following. Let us say that we have a stream of charge with a voltage of 0, and then we have another stream of charge with a voltage V1, and then we have, let's say we have another stream of line with a voltage V2, then how the electric field would look like? Look carefully. I drew it in such a way so that the voltage always varies in the x-axis. So let us say this is our x-axis, and this is the y-axis. And I say that the voltage is always same along a long stream. So if you change the magnitude of y coordinate, if you change the vertical position, there is no change of voltage. The voltage will only change if you go to the x-axis. If this is how the voltage would look like, then the corresponding electric field would always be, as I say, the electric field is dV dx with x hat, dV dy with y hat, and dV dz with z hat. So could you be able to tell that where the electric field would be? Since the voltage is only varying along the x-axis. So that means if you take dV dy, it will be 0. Right? dV dy means if you change the y coordinate, whether the voltage is going to change or not. And according to the way I drew it, it says that dV dy is going to be 0. In the same way, dV dz is also going to be 0. dV would only vary if you change the x coordinate. So only this guy would survive if this is how the potential would look like. So in that case, electric field would only have an x coordinate, and all these other components would be 0. Right? So in that case, electric field would be simply dV dx, and its direction would be along the x-axis. Okay? Tell me the following. If I take a point charge, let's say with a charge quantity of Q, and the voltage, let's say, let me write it this way. Let's say at a distance d1, your voltage is, let's say, 10 volt. At a distance d2, your voltage is probably 5 volt. At a distance d3, maybe your voltage is 1 volt. So, did you notice that for a point charge, the voltage is same if you go around the circle with the center at this position Q, then the voltage would remain same. So this is why I drew a lot of concentric circles with the center positioned at the point Q charge. So if this is how the corresponding voltage looks like, the electric field would look like just radially extended vectors. Okay? So in this position, in this case, the electric field would vary in both x and y axis. In fact, if you drew it in the three-dimensional space, then electric field would vary in both x, y, and z axis. And the interesting thing to look at is that electric field is always going to be vertical. It's always going to be normal to those concentric circles. This concentric circle, it represents what is the voltage. And if you take any circle, go around the circumference, then the voltage would remain same. Okay? The electric field is going to be normal to all these concentric circles. Okay? So let me write it this way: that these are the electric fields, and these concentric circles represents the voltage. If you count very close to this point charge, your voltage is increasing. See? If you go further away, your voltage is going to decrease. Okay? Yes.
So if our lines, if our rings are denoting voltages, and we kind of know that voltages are like a potential difference. So we're measuring with respect to something typically infinity, right? Or we assume it's 0.
Mm-hmm.
So if we're measuring from a reference point of infinity to these lines, that is in the opposite direction of the E field. So why don't we denote it as negative?
So let us say that our test charge was probably here. Okay? And let us say this test charge is +1 coulomb. And we have a positive charge sitting at the very center. If we try to bring that small test charge of 1 coulomb close to this point source, are you gonna see it like? Are you gonna spend more energy, or this guy is gonna very easily flow to this point charge? You're going to spend more energy. And why you think you're going to spend more energy? Because both of them are positive charge, right? This guy and this guy both are positive charge. That's why you have to spend energy to bring these small test charge close to this point source. Okay? But if it was negative, then you actually gain energy. You don't lose energy, you gain energy. So it really depends on that what is the magnitude and the sign of these charges. Okay? Is it what your question was? Or it was something different?
Well, no, that was a long, it was a long story. Never mind, I'll think about it.
Okay. Okay. Yes, go ahead.
When you think about this, you have like the higher voltage closer to the center, lower voltage going out.
Mm-hmm.
So kind of the rate of change of voltage as you go out is decreasing.
Mm-hmm.
So why is the electric field not negative?
So, electric field is always pointing to the radial directions, right? No matter whether it's a positive charge or negative charge. The direction of electric field would depend on the sign. If it's a negative sign, it's always electric field would be along these directions. it will be pointing inward. If it's a positive sign, then it will be pointing outward. Okay? But apart from that, their distribution will remain the same. Okay? And look at that. If this is positive, you take a test charge, this is positive. That means if you need to bring the test charge from infinite to some distance which is close to this point charge, you have to spend energy. That means the corresponding voltage must be positive. If you take a negative charge and bring that negative charge from infinite to some distance, then this guy will be negative. This voltage will be negative. Okay? So it really depends on what is your test charge, what is their sign. Okay? All right. So, as I say that we often need to understand from an engineering point of view that what is infinite. And I think you guys have previously explored the idea of voltage. That's why you know that a voltage is defined between as a potential difference between two different points. And typically the definition goes from if you take a test charge from infinite, bring it to the close distance of a coil charge, then the corresponding amount of energy you spend is equal to the voltage. But what is that infinite thing? Do I really? Let's look at these guys. We have a power socket with a positive and negative charge. When we talk about the voltage, do we really think that we need to take a test charge far away and bring it here in order to define the voltage? There is no such thing as infinite. It's all here. It's all very finite thing. So how come voltage is defined with the notion of infinite distance? It must be something that is finite. So how the voltage is related to some finite distance, that is something that we will discuss in our next class on Wednesday and the following week. And we'll try to explain it with some experiment. Yeah, so I hope that those experiments will clear up some of the confusions. Okay? All right, so I think we can close our discussion today. Good luck with your tomorrow's exam. Again, don't forget to bring your laptop and bring it fully charged. Thank you.
Going to the left. So I have to go to the other so I can Google Meet.
For free? Google Meet for free? You coming out there?
Yeah, I have to first check because if there's four in there, I'll just go to the open one.
Well, this happened?
Maybe?
Do it.
I also want to go to my secret.
No, not allowed. Not allowed.
Going to my secret
Yeah, so basically any integral you do, right?